This is a brief presentation of the technical portion of the MACA MIT Campus Decarbonization proposal. It is a techno-economic solution. The bottom line is there is a zero carbon solution. What we're presenting, we believe, is the lowest cost solution. It is available at MIT from all the analysis we've done and all the review of experts in this field that we've spoken with. And it's available for MIT to lead with as well, because this, in fact, is the front edge of this field and includes some pieces that aren't in wide use yet at all. We'll briefly go through the economics of heat pumps, give an application example, show what the technology is behind that, show the proposed MIT plan, and then give a comparative analysis of the CAPEX and OPEX and how they relate to these various choices. And we think the spectrum of layout will help anyone understand completely what we're trying to present. This is a report done out of Canada, and there's a quarterly report now out of the United States that says basically the same thing, that fundamentally, if you compare how are we going to decarbonize our society, and how do we get to that goal? And we've got this options of 100% air source heat pumps, and these are high-end cold climate rated systems. These are the top stuff, versus 100% geothermal and using the lesser technology of geothermal, so slightly lower grade, less expensive heat pumps. And shows that if you do that, it will cost more for the geothermal. But with the IRA funding right now, and that's refundable to places like MIT, nonprofits, and government, in fact, this will cost less now than air source solutions. And then we have this other perspective, which is important to understand, especially for an MIT, which is its own full grid solution, one way or the other, whether you're PPAing the power or however, that in fact, this using geothermal is how you lower the overall cost of the solution. And this has to do with understanding peak loads and such. These geothermal is thermal storage on site. In the case of geothermal, it's in the earth. And that it makes a huge difference. So it's a question of, are you going to spend money on electric batteries, or are you going to spend money on thermal batteries? It's the fundamental trade-off there. Thermal batteries are the far lower cost winner. So here's an example of one of the early net zero energy schools in this case. This was an engineer in Texas, a man named Don Penn, who we've recommended, who actually had put in a whole lot of geothermal at this point. So he learned how to do geothermal for the same initial cost as conventional four-pipe systems. And it has to do with some very specific things about how he eliminated central pumping and eliminated the steel. He's done several things that are very specific to these low-temperature solutions. And then you combine that with investing in your renewable energy sources, which of course is what we're all doing and you are doing. Then you end up with a solution that actually makes a profit over time relative to the other options. That is a game changer. Nobody thought about buildings and energy in this way before. So this is a fundamental change. And you got to start bringing these fundamental change ideas on board to understand where this is going. This just to show you there's that school that we just showed you. And it shows that it has extremely low EUI, in fact, a negative EUI. School makes money. Scratching the surface now, looking behind that application level at the technology. This is a graph showing the different kinds of air source heat pumps and ground source heat pumps. So these are the heat pumps available, and how much they cost to run. So this is dollars per square foot, EUI, and versus the outdoor air temperature. So this is a common graph for HVAC people, but not to everyone else. The bottom line is as it gets colder, it costs more to run. And when you're talking about these air source heat pumps, it costs a kind of a steep curve because the air gets really cold. And so you're having to suddenly get down in these low operating efficiencies, higher cost. And in the case of the older air source heat pumps, which is why heat pumps have a bad rap, is they cut out at about 20-something degrees or higher. And so all of a sudden you have to go to this coefficient performance 1 electric strip, which is not a solution we can afford on any level. But the comparison here is that this was an ASHRAE study, is that even in this particular building where they took floors and built one out VRF and one out higher grade VRF, lower grade GHP, geothermal. The VRF, even the high grade stuff, cost more than double to run for the year. And this system wasn't even designed well. This loop was out of balance. We could get into that another time, tell you all about this. This can even be done better than this. And so then the additional cost is, well, what does it cost in the winter peak to have the batteries to run that versus that? See, that's a big difference. So moving to MIT, The problem at MIT is, number one, ventilation, because there is an awful lot of exhaust going on. There's a lot of exhaust on any commercial site, but at MIT, in place for a lot of labs, this is really disproportionately the highest part of the load. By our estimate and our analysis, our work that we've done in the D Lab on Building 76, we estimate that perhaps 50% of the HVAC load in this campus is exhausted, straight out stacks and exhaust vents. So that's the number one part of a decarbonization solution, is to bring in active energy recovery in the exhaust systems. And a lot of people think this can't be done, and they're not right. Okay, so we've laid this out. The students have presented it. This can readily be done. Then we complement that with converting the central chilled water loop pipe to an ambient loop. All that means is you remove the thermal constraint. You go from a 42 to 45 degree outgoing temperature, and you say, we don't care what it is. Anything between 40 and 90 degrees is fine. These heat pumps will all run on those temperatures. That's all fine, maybe 42. Just got to make sure you don't freeze things. But this is, so it's a heat pump solution in the exhaust recovery and a heat pump solution for the buildings, all connected to this ambient loop. That way you get this maximal diversity going on campus. So you get diversity across a building, to the side that the sun's shining in on, the side that's not, no sun, different rooms, different temperatures, and around the campus, all the different kinds of loads, like dining facilities versus labs versus offices versus residential. And we know the residential is not on this chiller loop yet, but it will be eventually. So that's a heat pump solution. And that, with what we also bring, which is actually adding additional capacity in these exhaust systems, so that you take advantage of this high volume of exhaust going on to essentially turn those into air source heat pumps. So then you've got air source heat pumps also connected to your chilled water for any time it's not a peak load time, peak temperature time. You can be gaining just air source input into this thermal system. Now, we will be going to adding ground component of some kind. Now, there's a reason for that. And it has to do with, when you model this stuff up and you look at it over time, you'll find that there's these spiky loads and whatnot, and there's this big annual load shift. And you've got to balance those out, or you have to oversize all your equipment and you have these giant electric demands. So ground portion is needed, but exactly what that ground portion is, now that's up in the air. And this requires more modeling and analysis to understand this balance. In fact, any geothermal system, which is this ground heat exchanger part, has that. For MIT, we're bringing a very specific approach. After analyzing the ground at the site, I'm a certified geoexchange designer. This is what we do. We analyze the ground at the site. Then you figure out what is the right solution at this site. And in this case, there's some questions about drilling this argillite, which is 100 feet down and deeper. And we have found that some drillers have had some real problems with this. So our first order of business is to go, well, why not just come up with a solution that doesn't even get into that? And so that's where these thermal batteries come in. This is some new cutting edge work in this field, generally pioneered by Dr. Xiaobing Liu at Oak Ridge National Labs. Though there have been other people doing this, and there's people doing this in the form of building thermal piles now in concrete and whatnot. But this is an aftermarket application where you bury a tank, basically a vertical tank in the ground, and you fill it with some substance that's got like multi-phase. Then it's got a crystallizing substance that crystallizes somewhere in a convenient temperature for you. Then you get both the thermal storage of the tank, you get the thermal storage of the phase change, and you get the thermal storage from this very substantial surface area connection to the ground. And in the case of MIT, this is fully saturated ground because it's a flooded, dam backed up river. So this is a very efficient solution. And it's our belief that this alone could be the entirety of the solution. Just take the idea of thermal tanks, spread them out around campus, bury them straight down 100 feet, very low impact, designed and intentionally done so you could just cordon off a little 20 by 20 foot area, do this work, completely repair it, move away. You'd never even know it was there. All gone, all buried, all below sod. Now, there's other things we can do. We've got to do some additional. We need a test bore to find out if we can do this inclined drilling. This is an innovative process out of France, where another place that has a similar kind of ground around Paris has this deep mud. And so these guys are specialized in doing deep mud drilling and specialized in doing potentially this very soft argillite. We need to get a test bore in there from them And they're on the student MACA team as well as the gentleman taking an MIT MBA course. And so we need to find out if that's an available solution for us in this campus. And then there's also the option, though we would never do it under the wooden piles. This is just showing you what we're talking about. There's also ways to do directional boring in this soft overburden that's above the argillite under MIT. So there's multiple ways to do this, none of which are what we would call conventional geothermal, and none of which involve loop fields of tearing up any place. This is all very low impact work. These guys move in, they need a 50-foot radius. We believe this needs probably a 20-foot radius or 10-foot radius to do a 20-foot area to do it in. And so we've come up with these very low impact approaches for MIT. Now, let's take another look just to try to get everyone's head around this and understand these trade-offs of what these different decarbonization options are. This is what MIT has now, a gas solution. It's not a decarbonized solution. It's not a winner. It can't be done. Can't be decarbonized. The same is true with the low-end air source heat pumps, and it has to do with the fact that they drop into that COP1 strip. We'll never be able to afford to build that grid, excuse me. Can't be done. So the solutions are going to be somewhere between high-end air source heat pumps and geothermal, and somewhere in between here. And this is good to understand how these things trade off. So the air source heat pumps cost more to run, the geothermal costs the least to run, and the stuff lasts a very long time. The ground loop, for example, has a official over 50-year life, but nobody really knows how long it'll last. It's very long, longer than steel, and a lot longer than steel. And then, but the geothermal costs more. The installation is here. But now, right now, with the IRA, that's not true. Right now, with the IRA, the geothermal costs the same to install. So we're in a different paradigm here in today's world. Now, moving a little further, bring in this idea of the grid and this whole idea of thermal energy storage. So there's no thermal energy storage here. It's just using the air, which will be very cold in the winter, very hot in the summer. This uses the deep earth, a very stable temperature, year-round, which is your average air temperature, thermal energy storage. And there's other classes in here. And what we're trying to show is how these all relate to the installation operational cost, as well as the net decarbonization cost to our society, which includes the grid, which of course we're all going to pay for. You and everyone else is going to pay for this one way or the other. And so there's an entire class of solutions in here that we believe at this point, but Xiaobing Liu at Oak Ridge National Lab has actually demonstrated this, and others have as well, that produce solutions similar to the ground loop, the deep ground loop, but aren't that. So right now, though, at the other end of the spectrum is water tanks, which is what a lot of people have done already for thermal energy storage, and what we understand a lot of people try to do in central plants too, big tanks. And so that is a solution. It's the minimum entry point for thermal energy storage. But there's more in here, and that's where these thermal batteries, this advanced work out of Oak Ridge comes in. And we're suggesting that there is a sweet spot in here. This between these two, very low impact installation that is a heat pumps with thermal energy storage that is in fact ground coupled thermal energy storage, but not this Warfield kind of thing that other people do. So that's what we're looking for. And the research out of Oak Ridge suggests at this point, which is what we're modeling and trying to prove now, is that in fact, this produces an operational cost point that's even lower, because it lets us take advantage of the periods of extremely low grid power cost and utilize that when it would be otherwise expensive. Like, think about just every single weekend during the day, there's an awful lot of PV that's going to be on the grid, and there's not going to be a load for that on Saturdays and Sundays and holidays. And so that stuff is going to be dirt cheap every single week. And this is not a hypothetical. There's already large periods of time now in California and Texas and whatnot where there's power is below zero because there's been a lot of net metering and stuff. This is why net metering is going away. It's because there's a lot of times where they'll pay you to take power off the grid. So there's this whole dynamic with the clean energy generation that's involved in this and trying to understand what is the optimal solution. This is the bottom line. We're looking for what is that ideal maximum installation cost, which we're saying is down here, no more than what would air source heat pump be, but we're getting this much better operational cost. And then this overall cost to our society, including people like you who have their full grid responsibilities and whatnot. You're buying your power from PPAs, from solar and whatnot, maybe from wind. That there's this net minimum cost that will be much lower than air source heat pumps and much lower than just tanks. And those two factors are what we're looking for in this work. Again, that's all about designing these parts. And this may be municipal water and sewer connection, but this requires the municipality to be part of that. And the MACA team is in discussions with Cambridge Water now to see if that's possible. This has been done other places, very inexpensive to do. Essentially, you're utilizing their buried pipes as a ground source. That's how it works, whether upstream or downstream, you know. And again, this requires design. You can't hip shoot this stuff. You can't just go, oh, well, that's what this costs. It's like, no. And so all the engineers have told you, oh, geothermal, so geothermal's this, geothermal's that, period. They don't know what they're talking about. I can tell you as an expert in this field. So that's what it's about. It's about finding that sweet spot. What is that capability that we're looking for there that's the optimal solution? And to review its techno-economic solution, you've got to understand both sides of this to understand the value of it. That in fact, there is a zero carbon solution, no questions asked, it's been done other places already. It is the lowest cost solution, which there's other campuses that MIT is going to be talking to about this, where this is already happening. And it's available. And it's available for MIT to lead with. This advanced part of this, understanding these thermal batteries, understanding the grid interactivity, and becoming part of a transactional market for energy across the whole thing, the whole grid load storage system. That is available work in R&D. And in fact, what we're involved with and what we're presenting on ASHRAE, for example, on this material this summer. Thank you.